Hey guys, welcome back to Foundations of Science, section on earthquakes. Today we're going to address the question of what is an earthquake? So this is obviously some damage due to an earthquake. This is from the earthquake in Iran, a town called Bam, B-A-M. Can't remember exactly which year it is. I'll check on that and get back to you. Last time we talked about the different kind of plate boundaries. We have these transform plate boundaries where you've got two of these lithospheric plates sliding past one another. We've got divergent plate boundaries where we've got two lithospheric plates separating from each other, and we've got these convergent plate boundaries where you've got one piece of lithosphere that tends to be a little bit denser than the other one that gets thrust beneath the usually continental crust in this case. And you'll recall also that the convergent plate boundaries are where you end up with the largest earthquakes, but as we'll explore, not necessarily the most damaging. We also talked about last time how strength of the lithospheric crust increases as you go down in depth, but then you get to a certain magical number. In the case of average continental lithosphere, about 15 kilometers, then the strength rapidly drops off as you get into more plastic type material that instead of when you hit it with a hammer it makes a crack, you hit it with a hammer it makes a thud. This arguably is not really a asthenosphere, it's just weaker lithosphere, but we're getting to the woods a little bit right now. We don't care about that much right now. What we do care about, however, is where that particular depth is in the different types of margins and how that's going to affect the size of earthquakes. So the three different kind of plate boundaries produce three different kinds of faults. Divergent plate boundaries produce normal faults. These tend to be high angle, tend to be in high heat flow areas, so therefore the brittle ductile transition tends to be pretty shallow. Reverse faults, these low angle thrust faults that tend to occur in convergent plate boundaries, sometimes in subduction zones, sometimes in places where two pieces of continental crust bang together and they don't actually subduct, like in India and the Himalaya, tend to be low angle faults, and the brittle ductile transition here tends to be a little bit deeper because you have colder material that's being pushed up on top of other colder material. And transform faults, these strike slip or transform faults, tend to be kind of your average crust. They're probably about 10 or 15 kilometers deep, and they slide past one another on these transform plate boundaries. If we look at heat flow in these different areas, we can look at what they call the geothermal gradient. The geothermal gradient is how fast does temperature increase as you go down with depth. If you look at the normal situation in A on the left-hand side of your screen, you can see that the geotherm increases about 10 degrees per kilometer. If you go into a place at a mid-ocean ridge, you've got extremely high heat flow. I mean, this is a place where the mantle is just cranking heat up to the surface of the Earth. So much heat that it actually melts the crust pretty close to the surface. You get little volcanoes, you get those black smokers that put smoke up into the dissolved minerals that look like smoke into the ocean areas, and you have the hydrothermal vents with those funky animals that live there. And there's enough vigorous convection there that happens that actually causes traction and pushes the plates apart from each other. In this area, you have incredibly high heat flow, so really close to the surface, you can have temperatures approaching 1,000 degrees centigrade. If you go to a hot spot, ironically with the name, you think it would be hot. It is warmer than your normal crust, but it's not nearly as hot as mid-ocean ridge. Your source of heat is much further down, and therefore the heat has more room to kind of diffuse out away. However, individual plumes can come up and make volcanoes, and of course the temperature of those volcanoes locally can be quite hot, but kind of more regionally it's not so big. We're not so much concerned about hot spots in this class because really they're not plate boundaries, you're not going to get big earthquakes there. And if you look at subduction zones, I would argue with this geothermal gradient a little bit. It's probably not quite as steep as shown here, where you can actually end up with refrigerated crust, where there's actually really cold crust as you go further down, and that can actually depress the depth of that brittle ductile transition. One thing, geologic aside here, I gotta get into the rocks a little bit because I'm a rock guy. One thing you'll notice different about this graph on the far right, the green line that there is what they call the solidus. This is the temperature and depth at which rocks melt. It's just like a phase diagram you might have seen in high school chemistry. So if you look at the normal situation on the far left there, If you're at 50 kilometers depth and say 2,000 degrees, you're going to be in magma. If you're at 50 kilometers depth and the temperature is 1,000 degrees, you're going to be in solid rock or something approaching solid rock. But curiously, on the subduction zone on the far right-hand side of the image, something strange happens to that solidus. It actually gets reduced. So where previously it would have taken you to be at what, maybe about 1,400 degrees Celsius to melt rock at 50 kilometers in that one, now it's like you can melt rock at 50 kilometers at only 1,000 degrees. So 400 degrees cooler, you're actually melting rock. What's up with that? Let's talk about that in class next time. This diagram, it's often called a sail diagram, is actually done by my master's advisor in New Zealand, a guy named Rick Simpson. It's a little hard to read, so stick with me. But if you imagine the top axis on this is strength of rock, and the vertical axis is the depth at which you can measure the strength of rock. Now, if you are at 5 kilometers deep there, you can see that in normal faulting area, the rock strength is maybe, what, 30, 40 megapascals, much stronger in a strike slip regime, and even stronger in a thrust fault regime. So a thrust fault regime at 5 kilometers, you're looking at daggone near 150 megapascals for the strength of the rock in that area. So it's going to take a lot more to break a rock in a thrust fault area than it would in a strike slip or normal fault area at 5 kilometers. So when you have, we'll talk about this a little bit more later, when you have these plates that are moving past each other, it's going to take a certain amount of strength to cause these rocks to break. The more stress you build up in this area, it's going to be based on the strength of the rock. So when you release that stress, you end up with bigger earthquakes. So again, a thrust fault area at 5 kilometers, if you're to break it at 5 kilometers, it would take an awful lot of strength to break that rock, but not so much at the normal fault area. So when you do get an earthquake in a thrust fault area, it's going to take a lot of energy to break that rock. When dealing with rock types, we're looking at how rocks respond to stresses or how they respond to different forces applied to the rocks. We're looking down, imagine we're looking down on a surface of the earth, and the line going vertical through the middle of this rectangle is a fault. If we apply a stress, we're pushing the left-hand side up and the right-hand side down. Eventually, rock is actually going to move a little bit. We call that elastic deformation, because if we were able to take that stress off, it would simply just go back and spring back to its normal position. So it's non-permanent deformation. But if we keep that stress applied, it's going to maintain that, but you're going to end up building stresses up on the weakest point, which is the fault in the middle. If we carry on, you end up straining it a little bit more. You're causing more and more displacement on this rock, but it still hasn't exceeded the strength of the rock. Keep going over many, many years. Eventually, you get to a point where it's really stretched out. It's like you're pulling on a rubber band so hard, it's just about ready to snap. If you're able to take that stress off, I'll remind you that it'll go back to its regular shape. In this case, it's ready to snap, and eventually, pow! If you pull it just a little bit further, it's going to snap, and that snap is what is an earthquake. Think about that snap. You actually hear that sound. That is the release of energy from that system. I want to show one thing from this. If we zoom in on the area of where that displacement, where that fault actually ruptured, the distance between the different sides of the fault in this case is what we call displacement. And we can calculate that pretty carefully based on the velocity that the plates are moving past one another, how fast they're shifting past each other like this, and how long they've been moving since the last earthquake. Very simple calculation. In the case of major earthquakes on strike slip faults, in this case, can be on the order of single meters up to tens of meters.